This is the second section in the vectors chapter, and this is vectors in 3D. And basically what we're looking at is the different notation we can use to represent a vector in 3D, and it's the same type of notation that we've used in year 12 vectors, but just with an extra number. So three different ways actually that we can represent a vector in 3D. So representing vectors. So we can represent a vector as a coordinates, which we've done already. So x, y, z. We can represent them as a column vector, which basically just places the coordinates stacked one on top of the other, or using the I, J, K notation, in which case we would have our value of x in front of y plus, in front of I, our value of y, our y coordinate in front of j, and our z value in front of k. And you can interchange between them, but some questions it may be easier to represent it in one form over another, and you often find that the column vector form is really useful. Sometimes the I, J, K notation, and you might sort of flip between them. It all depends on the question, but they all represent a vector or a point or a vector in 3D. They can be represented in different ways. Now all of these are with reference to the origin. Okay, so these are what we call position vectors. Yeah, so a position vector is in reference to the origin. Now you can get something called a displacement vector, and what a displacement vector is, it's basically how you get from one vector to another. Yeah, so if I had a point A here and a point B here, how I get from A to B, this x, y, z, okay, this is what we call a displacement vector. So it's how we get from one place to another. So a displacement vector is not the same as a position vector. A position vector tells you where are you in a particular place, what point are you in reference to the origin, whereas a displacement vector is how are you getting from one point to another. And we're going to look at some examples of displacement vectors in a moment. Now up here you'll see something about I, J, K. Now you remember I, J and K, they are these unit vectors, and unit vectors which basically point along the x, y and z axis, so I, J, K, like this. They're only one unit long, so the actual x-axis carries on like that, the y-axis carries on like that, the z-axis carries on like that, so they're just one unit long. So what we have here is basically these vectors represented, these unit vectors I, J and K represented as a column vector. So the vector I basically is one in the x direction, nothing in the other two. The vector J is one in the y direction, and the vector K is one in the z direction. So that's basically how they're defined. Okay, so in this question here, we've got these 2 points A there and B, and it says find the position vectors of A and B in IJK notation, right? So that should be nice and easy. So A would be I. We don't need to put 1I, just like in algebra you don't put 1x, you just put x. So that's 1I, I, plus 5j minus 2k. So that's A. And B, now you could put 0i, but like algebra you don't need to. You can just start by putting minus 3j plus 7k. So when one of them is 0, you don't need to write it down. You could do, but it's not necessary. And part B, find the vector AB as a column vector, right? So what we're finding here, A to B, this is a displacement vector. This question is asking, what's the vector that takes you from A to B? Now there's a couple of ways of doing this. So one way of doing it, the vector A to B is actually the position of B, which is that OB, minus the position of A. So remember what I said about a vector, a position vector being in reference to the origin. That's what this is, from the origin to B is basically the vector B, and the origin to A is the vector A. So if I do O to B and take away O to A, I will get that. Now O to B is just actually this 0, negative 3, 7. Now it says give the answer as a column vector, so I'm going to write my work in as a column vector. 0, minus 3, 7. So that's OB. Minus OA, which is 1, 5, minus 2. So I just do the top row minus the top row, so that's negative 1, 0, minus 1. Negative 3, minus 5, minus 8. 7 minus negative 2, which is 7 plus 2, which is 9. Okay. Now I've actually got a much easier way of doing it. Well, I think it's the easier way. So, Mr. Hines, hack. Right, my hack is this. And it's sort of common sense in a way. If I want to find out how to get from, let's draw a little diagram. Let's say I want to find out, I've got point A and I've got point B here, and I want to know how to get from A to B. Well, surely if I just look at the jump that takes me from there to there, that's the displacement, isn't it? Just the jump. What does the X go up by? What does the Y go up by? What does the Z go up by? And that's what I'm going to do. And actually then you can just write down an answer without really having to do any working. So if I do it that way, what I do is I look at the X part here, or the I part, and the I part there. What's the jump? Let's put some things on here. What's the jump that takes me from there to there? Well, this goes down by 1. Okay, how about the second one, the J or the Y? Okay, that goes from 5 to negative 3, so that goes down by 8. And how about blue? And this one, okay, the K part or the Z, that's going from negative 2 to 7, so that's going up by 9. Okay, there's my answer. The jump from A to B is negative 1, not negative 8, negative 1, negative 8, 9. Can you see you got exactly the same? It's the same. Yeah, and that was actually easier. If you work out the jump between where you're starting to where you're going, that gives you a very quick way of finding what that displacement vector is. So make sure you understand the difference between a position vector, that's what we had in part A, and what we had in part B, which was a displacement vector. And a displacement vector tells you how to get from one point to another. Now, just like we did in 2D with vectors, we can do multiples of them, add them together, and they're often easier to do when they're written as a column vector. So my little tip here would be, when you are finding multiples of vectors, like we're doing in part A, it is easier to do if you write the vectors in a column, yeah, or as a column vector in a column vector. Let's change that. Let's get my English right. Write vectors as a column vector, and they're already given as column vectors. So the first part of part A basically means 4 lots of A, so we can write it like this, plus B, 1 lot of B. So it's nice and easy to work out the first one. So you just multiply the numbers in the brackets by 2, and then we're going to add these ones, 4, -2, 0, and then we'll get 12, -8, 10. Yeah, boom, easy. Right, part 2, we're doing 2 lots of A, 2, -3, 5. We're taking away 3 lots of B, so 4, -2, 0. So multiply the first one by 2, so 4, -6, 10. And we're going to be taking away 3 lots of 12, -6, 0. So 4 minus 12, -8. -6 minus -6, -6 plus 6, 0. 10 minus 0, 10. Part B, state with a reason whether each of these vectors is parallel to 4i minus 5k. So it basically needs to be like any multiple of that is parallel to it. Now, do I have any vectors which are parallel to it? Yes, I do. This one, okay, because if I take, God, that's the worst arrow ever. Let's try again. There we go. If I, and let's tidy up that 8, if I multiply that 4i minus 5k, if I times it by -2, then I get that vector there. So my reason would be that -8, 0, 10 is parallel to 4i minus 5k because 4i minus 5k, -2 times that equals that vector, which is written as a column, okay, and you know that they are equivalent. Magnitude just means size, so that means finding the doing Pythagoras on it, and hence find this A with a little hat. Now that's what we call a unit vector. Now unit vector has length 1. Now how do you find a unit vector? Well, if you have a vector, if you divide it by its length, then you get a vector of length 1 which is in the same direction. So you preserve its direction, you change its length. So if we take any vector, we divide it by its length, yeah, we get this unit vector which has length 1. Now if the proper notation is, if our vector in our case is A, so we've got our vector A, the length of the vector, or the actually let's write it down as A hat here, so this little unit vector is equal to the vector, okay, that's just A, divided by its length, and that modulus sign means find its length, and the way that we find its length is we do Pythagoras. So let's do that, so we need to find the length or the magnitude of A. So we could write it like this. The length of A equals, so it's going to be 2 squared, don't need brackets, 2 squared plus -1 squared plus 4 squared. So that's going to be 4 plus 1, 5, 5 plus 16, that's going to be 21. So root 21 is the length. So A with a little hat on, the unit vector is going to be, now we can write this in different ways. So we basically need to divide A by root 21. So we could write it like this. We could write 1 over root 21 of 2i minus j plus 4k. That's one way of writing it. Or we could write it as 2i minus j plus k all over root 21. Or you could write it as 2 over root 21 I minus 1 over root 21 j plus 1 over root 21 k. So you could write it any one of those three ways. They're all acceptable. It all depends on the context and the questions. I think that's probably the easiest one to write out, but they're all equivalent. So you decide which way you prefer. All of these now are unit vectors. The direction is preserved, but the length is now just 1. Right, this question is asking us about finding the angles between a vector and each of the positive coordinate axes to 1 dp. Right, let's write these down and we can have a little think about it. Let's say I've got my a vector A, yeah, and that vector is something x, so I could write it either as x, y, z like this, or it could be x, y, z like this, or it could be xi plus y, j plus z, k. And I want to find the angle between this vector A and, let's start with the x-axis. Okay, so let's put here angle between A and, so the first one's going to be the x-axis. Now the cosine of the angle between the vector and the x-axis is equal to the x part of the vector divided by the length of the vector. Yeah, so the cosine of the angle between a vector and the x-axis, that's why I put a little x there, is equal to the x part of the vector, so whatever that number is where x is, divided by the length of the vector. So you would do Pythagoras to find the length of that vector. So that's for the x-axis. For the y-axis, very similar, it'll be the cosine of the angle between the vector and the x-axis, the y number in the vector, again divided by the length of the vector, and then if I want to find the angle between the vector and the z-axis, the cosine of that angle is the z part of the vector divided by the length of the vector. Now, if you think about it, what is cos? Adjacent over hypotenuse. Adjacent over hypotenuse. If you were actually to draw this out, you would actually have, if you were to draw the axis and you were to draw a vector, you'd have a right angle triangle. The adjacent, well, that would be whatever this value is, the x value, the y value, the z value. The hypotenuse, well, it'll be the actual length of the vector itself. Yeah, let me try and draw that out. Let's say we've got our x, y and z like this. Okay, hopefully you can see that's in 3D, and we've got some sort of vector that's going up like this. So this is our vector A, and we want to, let's say, find the angle between that vector and the y-axis. So let's say we want to try and find this angle here, which we'll call theta. Well, you can see if I just sort of draw a line that goes from that vector that's going to go to the y-axis. I'm just going to make this a little bit shorter so I can do that and draw a line down here that's at a right angle. Then you can see where the working comes from. Yeah, so the length of A, that's going to be the hypotenuse of the triangle, and the adjacent, well, it's going to be the y value. So that y value divided by the length of A will give you the cosine of the angle. Now, because you're finding the cosine of the angle, you just need to make sure that you do the cos inverse or arc cos of whatever answer that you get. Right, so our vector A is 2i minus 3j minus k. We're going to need the length of A for all of these, so that's going to be the square root of 2 squared plus negative 3 squared plus negative 1 squared. Bad square root sign. So that's going to be 4 plus 9, or 4 plus 1, 9 plus 1, 10, 14 root 14, which I don't think can be simplified. So if we want to find the cosine of the angle between that vector and the x-axis, it's going to be the x part of the vector, which is 2 over root 14. Now what we'll do is we'll write these all down, and then we'll work them out, do the cos inverses of them. So notice on the second one with the y-axis, you can even put a negative in, it still works. Same here. Okay, so then what I'll do is I'll just do the cos inverse of those things to find what those angles are. Now we're in degrees. You would normally give the angle between two things in degrees unless the question states otherwise. So cos inverse of 2 divided by root 14, and we get 57.688. So 3 significant figures, and normally angles you'd give your answers to 1 decimal place anyway. So 57.7, that rounds to degrees. Let's just scroll back and change the 2 to negative 3. So then I get 143.3. So with angles, as I said, 1 decimal place rather than 3 significant figures. And let's change that negative 3 to a negative 1. And I get 105.5 degrees. Now, if a question said that they want the acute angle, then you would just do 180 minus the answer. Okay, so it just says the angle. So acute angle between a vector and an axis will just be 180 minus the angle, and that'll give you the acute angle if that's what was required. Right, so we have position vectors here, which are these two, and they're always relative to a fixed origin. Oh, they put that in, but position vectors are always relative to the origin. Find AB and show that OAB is isosceles, right? So let's find AB first of all. So A to B. So I'm going to do it my quick way. Is what's the jump from A to B? Well, the I goes down by 1, so negative I. The J goes up by 2, so 2J. The K goes down by 8 because it's going from 7 to -1, so negative 8k. So there we go, there's the vector that takes me from A to B. I'm just going to sort of draw a diagram to help me visualize. This in no way is to scale or anything like that. So we've got A, and we've got the origin. Maybe I'll call this one the origin over here. So origin, we've got point A and we've got point B. So we know the vector that takes me from the origin to A is this 4i plus 2j plus 7k. The vector that goes from O to B is 3i plus 4j minus k. And the vector that takes me from A to B, so it's actually going that way, these ones go that way, we've worked out as negative I plus 2j minus 8k. Now, if we want to prove it's isosceles, we should have two sides the same length. So we're now going to use Pythagoras to work out the lengths of each of the sides. So the length of this side, so the length of AB, well, that will be the square root of 1 squared plus 2 squared plus negative 8 squared. Now I think I'll be able to do that in my head. So that's going to be 1 plus 4 plus 64, so that's 68, so that's root 69, that one. So that's the length of AB. Let's have a look at the other two. So let's do this one here. So we're going to be working out the length of OB, and that will be the square root of 3 squared plus 4 squared plus negative 1 squared. So that will be 9 plus 16, which is 25, plus 1, which is 26. Okay, so doesn't prove it's isosceles yet until we've done the third side. And this will be the length of OA, and that will be 4 squared plus 2 squared plus 7 squared. So that's going to be 16 plus 4, which is 20. 20 plus 49. Ah, there we go. So root 69. So what can we say? So since OA and OB, or actually let's write it like this, since the length of OA equals the length of AB, hence, or therefore, triangle OAB is isosceles. Right, you should now be able to do exercise 12b on pages 341 to 343 of the textbook, and I'll probably just write down this again. I think this is probably the bit that you may forget. This isn't, I'm pretty sure this isn't in the formula book. So the angle between a vector and one of the coordinate axes. Yeah, so I'll just put those there in case they come up. And also I think the other thing that's useful is to know that the vector I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. That's useful.